Alrighty, welcome back to Fun Maths. Today we are looking at the derivative. Perfect. Alrighty, there is some information that we need to reconsider from earlier maths lessons. So if you first of all recall when we were looking at rates of change, we were looking about the notation or the chat about chords being a line segment between 2 points and a secant being a line through particular points P and Q on this curve here. Now, what we did look at was considering to get the instantaneous rate of change, making those line segments smaller and smaller. And so as you can see here, as we go from P to each of these Q, you can see as we go down to this one Qn, for example, or even smaller, that's going to become closer and closer to the instantaneous rate of change the smaller we make those particular secants. So, building upon that, let's consider the tangent to a curve at a particular point. So again, if you've got the function f of x equals x squared, so quadratic here, you can see here if you had a particular point, point A, obviously to find its corresponding y coordinate, it's going to be a squared. Then from there, they're saying, hey, if you were going to create this chord at another point, Q, then what you're going to be doing is you're going to be adding on a certain value. Yep. And so what you would do is for the x coordinate, you're going to be adding on a certain amount because it's a certain distance away. And so they're using the notation, hey, we're going to add on h here to that. Likewise, to add on h to this part here, you would do the a plus h, and because this part is squared, obviously it is squared also to find out its corresponding value. Now again, we haven't determined exactly what the value of h is. It could be fair way away, or indeed it could be really, really close. And so that's where we're going to have the chat about these things. So again, once you've established this, it's a matter of working out the gradient. We've said this before. Obviously it's going to be this value here, take away this value here on the top line, divided by this value here, take away this value here on the bottom line. So we've always said that. You might have done the coordinates as x1, y1, x2, y2, and use the formula y2 take away y1 over x2 take away x1. Same difference here. To continue finding out the gradient in this particular case, you would expand things out, as you can see here, and then simplify things down. Yep. So obviously here you've got the a squared, take away the a squared, they cancel each other out. You're then left with 2ah plus h squared divided by h. Yep. Now if you take on the top line here these h's, or h out as a common factor, you'll be left with h brackets 2a plus h, close bracket, over h, and then you can cancel out those h's, and we'll have a bit more of a chat about that later, and it will leave us with this here. Cool. So what we've done in that particular case is we're saying the limit of 2a plus h as h approaches 0 is 2a. So they're saying if you make this h value get really close to 0, or as it approaches 0, effectively if that's 0, you're only going to be left with this 2a here. Okay, that's what they're saying here. And so in that particular case, as that h value gets really, really small and approaches 0, you can say that the gradient of p is said to be just this 2a that is here. Perfect. It says the straight line that passes through the point P and has the gradient, or the slope here, of 2a is called the tangent to the curve at P. Alrighty. It says as well, it can be seen that there is nothing special about a here. The same calculation works for any real number of x, and the gradient of the tangent to the graph of y equals x squared at any point x is 2x. Cool. Now here is the terminology that we need to get our head around. It says we say that the derivative of x squared with respect to x is 2x. Or another way we can say it is the derivative of x squared is 2x. So we can shorten that down, and we'll talk more about this as we go along. Alrighty, here is the first worked example. It says here again, first consider the gradient of the secant p to q. It says find the gradient of the tangent line to y equals x squared take away 2x at the point P, and it's telling us the coordinates here for P are 3, 3. Alrighty, so if we've got the coordinates here of 3, 3, and we know here to calculate this y value we used x squared plus 2x. If there was another point h distance away somewhere, these would be the coordinates of point Q. Obviously, you'd have the 3 and you'd add on h to that. Perfect. That's where that one comes from. 3 plus h is Q's x coordinate. I'm doing the same here for the y value. To work out the y value, obviously we use this equation here, x squared take away 2x, but in this particular case it's going to be 3 plus h away. So wherever we see the x, we're going to substitute in 3 plus h. So here you'd have 3 plus h squared, take away 2 times 3 plus h, which will give us the y coordinate there for that. Excellent. So again, I've been harping on about this. You should be able to calculate the gradient between these 2 points. Obviously it's the y2 value here, take away the y1 value, divided by the x2 value, divided by the, take away the x1 value. So that's just writing it out in full. From here, it is a matter of simplifying things down. So we expanded out 3 plus h squared. We've also expanded out negative 2 times 3 plus h. So we've got rid of all the brackets on the top line there. From here, it's a matter of grouping like terms and simplifying things down. You've got 9 here. Take away the 6, take away 3. 9 take away 6, take away 3 is 0. So they cancel out. You're left with, on the top line, 6h plus h squared take away 2h. So that's these h's here cancel down to 4 lots of h plus h squared over h, which gives us this here. Now, this is where people can get a little bit stuck. The trick with these is to take out the common factor on the top line. So the thing that's common to both 4h and h squared is h. Then you're left with, on the top line, 4 plus h is on the top line. I've just taken out h as a common factor. H times 4 is 4h, h times h is h squared. And on the bottom line, you've got the h still from here. Now, the good news is by doing that and having the h out the front as a common factor, you can cancel things out. So what will happen is this h here will cancel out with this h down the bottom line, and you'll just be left with the 4 plus h that was there. Perfect. So now that we've got 4 plus h, yep, so that cancelled out with the h there. I'll show you quickly. So they cancel it, left with 4 plus h. Perfect. It says now consider the gradient PQ as h approaches 0. So they're saying, hey, if that gets really, really small, the h value, and it's a really, really short secant, and which is really close to the instantaneous rate of change, then we can find out what the tangent or the gradient of the tangent is at that point. So as h approaches 0, that really effectively becomes 0. You end up with 4 plus 0, which is just 4. So we can say that the gradient of that line, the gradient of the tangent line at the point 3, 3 is 4. Cool. Let's have a look at the next one. It's doing the same sort of thing again. It says find the gradient of the secant PQ and hence find the derivative of x squared plus x. This time, rather than having an actual coordinate, they've just listed x and x squared plus x as the coordinates. Obviously, if you're going to be h away from this here, adding on h to x, in the q value, where you have the x, you would rewrite it as x plus h. And here in the x squared plus x, wherever you see the x, you rewrite it with x plus h. So here you'd have x plus h squared, which they've done, plus x plus h, which they've written there. Perfect. Again, we write out the gradient between both of those. I've been harping on about this. This one, take away this one, divided by this one, take away this one here, which they have listed out in full. From here, it's a matter of simplifying things down. That can be expanded out. When you're expanding, getting rid of these brackets here, we multiply everything by -1. So that becomes negative x squared, and that becomes negative x on the end. That x there cancels out with that one. So you're left with just h on the bottom line. From here, we need to again simplify things down. Again, you've got this x here that cancels out with that one there. X take away x is 0. You've got x squared here, take away x squared here. It cancels out. You can see you're just left with 2xh plus h squared plus h on the top line divided by h on the bottom line. And again, as we've spoken about, if we do not do this simplification process, some people just leave it like this and go, okay, well, we'll substitute in h being 0, and we'll work out what the gradient is at that point. If you leave it at this stage and you try substituting the 0, ultimately you're going to be trying to divide by 0, and that's where errors occur, okay, because we can't divide by 0. Yep. So as always, you have to take out the common factor h out the front, and you'll be left with 2x. Imagine that's a, oh dear. Let's try text. You'll be left with 2x plus h plus 1 in the brackets, the h out the front. Yep. Now, if you've got h on the bottom line and you cancel those out, you'll end up with 2x plus h plus 1, which is there. So that trick to pull out h as a common factor is imperative that you understand that with these particular types of questions. Once you've got this here, 2x plus h plus 1, to work out the instantaneous rate of change or the gradient of the tangent line at that particular point here, we need to make h equal to 0. Yep, or as h approaches 0, it gets really close, it's the same as 2x plus 0 plus 1, which is just the same as 2x plus 1. So we can say there that's what the gradient is at that particular point. Perfect. Alrighty, next thing we need to have a chat about is sort of how we write this approaching 0 in mathematics. Yep. And what we need to do for that is we need to use what's called limit notation. So, for example, like what we just did, it says the notation of the limit of 2x plus h plus 1 as h approaches 0 is written as follows. So you write it with a lim as h approaches 0, so a little arrow that goes across to the right. So limit as h approaches 0 for 2x plus h plus 1 is written like this. Okay, so it's just, rather than writing it out and saying it in full, we just use this limit notation. It says here the derivative of a function with rule f of x can be found by doing the following. 1. Finding an expression for the gradient of the line through each of those points. So you will have point P, you will have the, for example, you'll have the x value and you'll have obviously its corresponding y value. And then if you've got another point Q somewhere off in the distance, we're adding a h amount to that x coordinate, and then we're also doing the same for the y coordinate as well. 2, we're also going to be finding the limit of the expression as h approaches 0. So after we work out the gradient, it's a matter of finding the limit as h approaches 0 for that particular function. So here is another example. It says consider the function f of x equals x cubed by first finding the gradient of the secant through the point 2, 8, and then through another point q, which is happening at this location. It's saying find the gradient of the tangent to the curve at the point 2, 8. Yep. So again, let's go through that process. Finding the gradient between p and q, obviously it's going to be this value take away this value on the top line, which they've done, divided by this here, 2 plus h, take away this value here. As we've been doing in the past, we expand out the top line. So 2 plus h cubed expanded out is as follows. And we can simplify as well the bottom line. You've got the 2 here, take away the 2 is 0, so you're just left with the h on the bottom line. Simplifying down this here, this 8 here cancels out with that 8 there. And you're left with 12h plus 6h squared plus h cubed on the top line. Here we are here. Again, you do need to continue further simplifying things down. On the top line, you need to take out h as a common factor. So h comes out the front of the brackets, and then you'll be left with 12 plus 6h plus h squared divided by h. Those h's cancel out, and you're left with 12 plus 6h plus h squared. Last part of this was saying, okay, we need to find the limit of this as h approaches 0. So we're going to use that notation that we just had a chat about. So you'd say the gradient of the tangent line at 2, 8 is, as the limit of h approaches 0 of this here, 12 plus 6h plus h squared. It's basically saying if you substitute 0 into here, you'd end up with 12 plus 6 times 0, which is 0, plus 0 squared, which is 0. You just end up with the 12. Okay. Now, again, here are some examples that will allow you to practice determining the limits. Yep. So again, if you're asked to calculate the limit as h approaches 0 for this expression here, really it's just a matter of substituting in 0 where the h is and evaluating that. So if you put a 0 in here, you end up with 22x squared plus 20 times x times 0. And that would become 0 plus another 0. They become 0. You're just left with 22x squared. Part B here, again, don't let them trick you here. If you just try and evaluate it as follows, you try and put in the 0 where the h is, and you go to try and divide it by 0, calculator or whatever you're doing will come up with an error because you cannot divide by 0. So remember, you have to take out the common factor on the top line, which is h. So h out the front, you'll be left with 3 x squared, that's squared, plus 2h. Oh dear, 2h. On the top line, when those cancel out, you'll be left with just, we've got 2h over h. So they cancel out, you'll just be left with 3x squared plus 2h. We can then evaluate the limit as h approaches 0 with this. So when you substitute 0 into h for just this part that's left over, 3x squared plus 2h, 2 times 0 is just going to be 0. You're just going to be left with 3x squared, which is this part here. This one here, oh, this is good. It says evaluate the limit as h approaches 0 for 3x. There's no h in here. Yep, so ultimately you're just going to be left with the 3x. Same sort of difference here where you have just this whole number, limit as h approaches 0 of 4. Again, there's no h to put in a 0 there, you're just left with that 4. Cool. Now again, these particular things can be done on your calculator. You can see here in the maths main section, if you had to calculate the limit of that there, you can use h as a variable from the keyboard. There is a limit button in the Maths 2 section, which will bring up this template. You can go find the limit of h as it approaches 0, filling it out for this, and it will calculate it for you. Okay, they could ask you to calculate the derivative using first principles. Now, calculating derivative using first principles is applying this information that we've been talking about. So if you're calculating the gradient of the secant between some points, say P and Q, we've said it's obviously going to be the function plus h, or x plus h, take away the original function of x, divided by the x plus h, take away this x value. Yep. So the whole idea of finding a point a little bit further on by adding on a h value is the whole idea of first principles here. So there is a formula that you can use. It says the derivative of a function f is denoted as f dashed. Yep. If you see f and a little f dash, what they're asking you to do is calculate the derivative of the function. And we can do this by, so f dash of x, finding the derivative, is calculated by working out the limit as h approaches 0 for the following, as we've been talking about. So let's have a look at an example applying that, which is called differentiation by first principles. So let's say you've got a function f of x, it's equal to x squared plus 2x. It's saying, hey, find out the derivative f dashed x by first principles. Alright, you would write out the formula for calculating the derivative by first principles as follows. Check. From here, what we're going to do is we're going to write out this function here, but where we see the x, we're going to substitute in x plus h. So, writing it out, you'd have x plus h squared, which they've done, plus 2 brackets x plus h. So this part here is where they've written out the function, but they've added on h to the x value. We've written it out. We put in the negative sign here, and then we write out the original function, which was x squared plus 2x. It's written out there. From first principles, it then says it is divided by h, which we've done down the bottom here. From here, like we've been doing in the past, it's a matter of expanding out this top line. So, expanding it out, we end up with the following. We then need to be careful about simplifying things down. So obviously here this x squared, we've got take away x squared, they cancel each other out. We've got 2x here, I've got a negative 2x here, they cancel each other out, which means you're just left with the 2xh plus the h squared plus the 2h here. So that cancels out with that cancels out with that, and you're left with those three terms there. That's over h. Again, I've harped on about it. This is probably the 5th time this video. Need to take out h as a common factor out the front. Pull h out the front. On the top line, you'll be left with 2x plus h plus 2. When you cancel those h's out, you'll end up with just this here, 2x plus h plus 2. We can evaluate the limit of this now by substituting 0 in here, and as h approaches 0, or gets really, really close to 0, it's effectively the same as 2x plus 2. So we can write down the derivative, or f dashed x, is 2x plus 2. Cool. Next one. It says here, for the function 2 take away x cubed, again it's saying find the derivative f dashed x by first principles. So writing out the rule for working out the derivative using first principles, make sure you write it out correctly. First up, we need to write out this function f of x, but we're going to be substituting in x plus h. We're rewriting out with x plus h where x is. So you'll end up with 2 take away x plus h cubed, which is this part. I've just written this out, but where x is, we've just put in x plus h. We then write out the negative sign here. Then we write out the original function f of x, which was 2 take away x cubed. Notice as well, good practice is to put that into brackets, because when you are taking it away and you're expanding it out, that could or will change the signs of things over here. So expanding things out, we've got the 2 take away x plus h cubed, that's been expanded out. Take away the 2 take away x cubed written on the end. From here, expanding things out, obviously that would become negative 2 and that would become positive x cubed. Again, multiplying through this negative 1 here, that would become negative x cubed, that would become negative 3x squared h, so forth and so forth. Once you've expanded all that out and got rid of the brackets and simplified things down, you'll end up with negative 3x squared h, take away 3x h squared, take away h cubed over h. Again, take out h as a common factor on the top line. You'll end up with negative 3x squared, take away 3xh, take away h squared. The h's cancel out and you're left with this here. We can then evaluate this limit. As h approaches 0, we're substituting 0 here and 0 here. That becomes 0. That becomes 0. You're just left with negative 3x squared. Perfect. Good news is, again, this type of thing can be done on your calculator. You could define the function as follows: f of x equals 2 take away x cubed, and then you can actually set up the function or the expression for the derivative. Yep. So remember, you can go evaluate the limit as h approaches 0. F of x plus h take away f of x divided by h. And so that will use this function of x here, and it will do that calculation for you and evaluate the limit, which could be helpful for checking out your working. Alrighty, thank you very much for listening. A little bit to get your head around, but I think that you will be able to have success. Bye for now.